Hey guys, today I'm just going to walk through the second lab that we've completed, or 02 lab, which is technically the third lab. Uh, there's just a common gotchas that a few of you ran into, so I think that this is going to be best demonstrated just by going through the lab and doing the problems myself, just so you guys can see, I guess, how I work through it. I'll be doing it completely live, so any errors that you see are going to be kept in, not edited out, and any Googling I do, I will be keeping in. In addition, I have installed a little keylogger here, so you can see what keys I'm pressing when they feel like that I'm doing some type of magic shortcut. You'll be able to replicate it, so I'll probably be pressing tab a lot, and maybe shift a lot. That's shift left, shift right, control, or never mind, it doesn't pick up that one. Control left. There we go. Okay, so say we just got an assignment, say it's lab 02. I'm going to open up my terminal, then I'm going to cd into uiowa labs jdken. Alright. I'm just going to do Jupyter Notebook from this directory. Open that up, open up 02. Open up this bad boy. Okay. So I'm just going to assume that most of the practice has already been done. There's one thing that I still need to do here. Okay. Make a mask on the functional image using the FSL mask command. So first make an image as the mean of all functional volumes. Alright, so with this I'll do FSL mas, and the input image is going to be the 01 lab. Like I say, I like to use tab a lot. OSF share. And sub. This is. There we go. And then we want to take the mean across time, so that's the tmean command. And then for the output, I'm just going to output everything into my current directory. Since this is the 02 lab, I'm going to put the output files into the current lab. So I will call this sub-97 underscore task flanker, and I'll say mean dot nai.gz. Okay. So I'll hit shift, enter, and that will complete that command. Then I'll do the second one where I need to binarize the mask, so change. Right now I have a mean image. We can take a look at it here right quick. Shift, click, Control C, Control V. Then let's do both those things at once. Wait for this. Okay. Sorry if I have a bit of a cold, and I might sneeze a few times while I'm doing this, but okay. So we're taking a look at the mean image here, and if I could see the intensity values, alright. That doesn't help. Well, let's see again. Gray matter is the brightest, white matter is a little bit darker, and CSF is the darkest. So, as we did in class, I am going to binarize the mask with FSL mas. Alright, I need to push that up a little bit. I think that keylogger might be more trouble than it's worth. Then I'm going to use that file, and I'm going to use percentage, and I'm going to choose the 90th percentile, so that'll threshold it to the top 10% of voxel intensities will be kept in, but they will be maintaining the original value. So if 900 was a part of the top 10%, then it'll still be represented as 900. So then, in order to squash that down into just ones and zeros to make our mask, we're going to use the bin option here. And now, I'll do click, shift, click, Control C, Control V, and now I'll just call this the flanker mask. And that should give us a binarized mask. And then I'll also open it up here so we can check it out. Iterative viewing of the stuff we make. So view, Control V, ampersand, why not? Alright, then we see mostly travels along the gray matter. So essentially this is kind of a rough approximation of a gray matter mask. Alright, so we'll call that good, and it's all ones and zeros. And now we'll plot it to inside here. So I'll take this, exit out, and I'll call that's my F mask. So I'll take Shift, Control C, Control V, take this out. Now I want the T mean one, so that's the F mean. Shift, click, Control C, Control V. Alright, actually, no, I don't think I ran. Did I run this? Well, I'm just going to run these again. Always important to run the prep. Okay, now let's see if that works. And there we see it again. So again, ones within the mask, zeros without, and the background is our epi image. Okay, so now I'll make my own ROI. Let's give that a go. Well, I'll do what Michelle did, and actually open up the file that I want to use. Except I keep clicking on things in accident. Okay. So again, Shift, click, Control C, FSL view, Control V, and run it. Okay, so now go to File, Create Mask, go over here, and instead of crosshairs, I want the mask tool. I'll make that 5 like she did. Then I'll just draw a little bit, and I'll go down a slice, draw a little bit, down a slice, draw. Okay, I think that's good enough. So now that I've finished drawing, just click on there, and I'll go to Save As, And I'll give this a more informative name since it's an ROI that's outside the mask. So I'll just call it the outside ROI. Why not? There we go. So I made that and saved it. So now, again with this, we're going to practice FSL mean TS. Okay. So FSL mean TS. Let's see if I remember all of the arguments to this. Okay, so input is going to be back in the 01 lab FSL share, or I mean OSF share. Boom. Sub. Bold. Alright. And then this one was -M for the mask, right? 3D mask. Alright. And then again move that so it's out of the way of the keylogger. I'm going to call that just the same mask. Actually, I probably should have named that brain mask. But we will do. And then output. Okay. And the output file name is going to be top 10 mean TS .txt. And this is just going to output in our current directory. This file is in our current directory, and then this file is back in the first lab. And then if I typed everything right, that should work. Let's give an ls here to see what all we have. So we got our mask, we got our mean, we got our outside ROI, we got our top 10 MTS. Alright. Let's see what it looks like. Boom. It's probably some scanner reaching the steady state artifact, and then at the end, probably some motion where the subject thought they were done, but they weren't done. Okay. So now the common gotcha in problem number 1 was selecting the highest 10% of voxels. So we've done that before as in the practice with regard to their standard deviation. Okay, so then we'll take a look at our FSL-MAS output here and see what we use to calculate the standard deviation. If I can find it myself. T standard, yeah, standard deviation across time. Alright, so that is what we'll be using to make our mask. So I'm going to combine, we actually need to do kind of 3 things here. We need to find the standard deviation, get the mean of that, and then we also need to threshold it to the top so that we only have the top 10%, and then we need to binarize that so that we have a mask. So I'm just going to combine that all into one command. So again, we need to pull from the 01 lab, 01 lab, OSF share from the subject's bold, and I will do TSTD for standard, and then I will take the thresh percentage 90, so it needs to be greater than the 90th percentile, so the top 10%. Then finally we're going to binarize. And then we can call this file sub-97, but not this. We want to call it standard dev mask. Yeah, I should have called the other one mean mask to be more congruent. But if I typed everything correctly, this should run. Nice. Okay. And then we are going to plot ROI. Let's see, we'll call, again, fmask is going to be equal to this guy. Yeah, so Control C. And then this will be fmask. Fmean is already defined from up top. I mean, I guess I should call this something different. S for standard deviation. Smask. And display equals ortho. And then if I think I plotted that correctly, okay, fmask, fmean, okay. Find out where I am again. Alright. So yeah, I'm just going to display it on the fmean, since that's usually the prettiest epi to look at. And I got an error. Okay. So let's see what the error is. The most error messages. Unknown property display. So I guess I'll display underscore mode. Okay. Mode. There we go. So standard deviation, the voxels with high standard deviation appear to be right around the edge. Okay. That makes sense to me because those are the voxels which are impacted the most by movement. Say if the person, for one volume, their head moved into that space. So we had the brighter voxels from the gray matter, then for another acquisition, for another volume, the head moved away, so then those voxels, instead of representing the brain, now represented the skull or the dura mater or someplace in between. So with the minute movements that we see within scanner, that the participant does within the scanner, they are picked up along the edges here, or at least that's where they're most visible. Okay. So yeah, we'd see a lot of standard deviation in those, and that makes sense to me. Oh, well, I guess I did that in the problem above. So I'm not going to do that again. But I can plot it. Now I just need to scroll up to remember what I named it. Where's my ls? There we go. That is the name I want. Okay. Just gonna call this one OMask for outside the brain. This is Python, so we gotta put that in a string. Can't just let it hang out like we can in Bash. Okay, without putting the quotes around it. And actually, I'm just gonna copy this. Control C, Control V. Change the S-mask to O-mask. Gonna keep the mean as the plotting background just because the mean is pretty. Alright, so that looks like it exists. And looks good to me. So I'll use the FSL mean TS to output the mean time series from the mask you've made on the functional image. High standard deviation. Okay. So we've already done the mean functional image. So that means we just need to write FSL mean TS commands for the standard deviation, for the voxels that are higher in standard deviation, and for the and for the ROI that is outside the brain. So let us draw out some of those commands. Mean TS, FSL, mean TS. The input is always going to be the 0, 1, lab OSF share, and that's going to be the sub, flanker bold, and again, input is going to be, I could copy and paste, but I guess looking at all the keys that I press gives you potentially an intuition in how I type. Not that it's the best way, but it's my way. Okay. There we go. And now the masks, now those are going to be different. Let's call this one, we'll call that one the outside. And this one's going to be the substandard deviation. It's always great to give comments. Those always are helpful. So I'll just say this one's the outside ROI, and this one is the standard dev command, so we can keep that separate. Then output, so that is what the previous file was named. Top 10. So this one's just going to be outside ROI, just to be consistent. Side ROI TS. I'll call this, I guess, the standard dev ROI underscore TS dot text. Forgot that scrolling doesn't work. Okay. Then if I run this, then I should have everything I need. So again, we'll just do, I'm just going to copy and paste this code. Except I will shift, click, Control C. Shift, click, Control V. Okay. So I'll give these all new names. So this is going to be the mean one. And I'll call this one the outside ROI one. And that one will read, well, first I'll copy all of this, Control C, Control V. And shift click, Control C. Control V. All right. And finally, there is the DF. Oh, wait. Okay. Just forgot the T here. Outside. And I'll call this one standard dev. And DF just stands for data frame. That's just what we call these data structures when we load them in Pandas. And I'll copy paste that, and I will take this, shift click, Control C, Control V. Okay. So I will be able to plot all these on the same plot. If I just keep saying the plt plot command, it'll just iteratively build on itself. Actually, I'm trying to remember if I can use dashes in variable names in Python. Well, I guess we'll figure it out. That might need to be switched to an underscore. But we shall see. plt.plot. Let's see. Can't assign to operator. Yeah. This needs to be an underscore. This needs to be an underscore. All right. So, yeah, plotting them all on the same axis, we can at least tell that there's a great variation in their average signal intensity. And I'm going to give each one a label so we can actually tell which ones are which. So I can use that with the label, saying this one's the mean, this one a label, this one's the outside. I'm going to give this one a label, and it's going to be standard dev. And then plt.legend, show that legend. Let's see. Okay. Yeah, it covers up a little bit, but we're good. So the blue is the mean. The outside is this what appears to be a straight line down here, and the standard dev is somewhere in the middle. So that makes sense if we think of the highest standard deviation voxels are sometimes a part of the brain and sometimes aren't a part of the brain. So if they're shifting in between the two states, then right in the middle, their average time series would be half in the brain and half outside the brain, which is kind of what we're seeing here. All right, and now let's plot them individually so that we can get a better auto-scaled view of them. So I'll do shift click. So I'll just do it one per. See. And this is going to require me to make one more cell, which is okay. And then Control C, Control V. Okay. Then let's looky here. Then we'll look standard D. Well, no, that's the outside one that I made, and that is the standard deviation. Okay. So yeah, we can definitely see that there might be some ghosting here at the end, but again, outside the brain, looks like there's nothing going on. Then here we can kind of see the same relationship between standard dev and the mean. So there's the drift is more apparent in the mean than it is in the standard deviation, but we still see the great peaks at the beginning and at the end. Okay. Well, that is walking through the lab. Made it with minimal errors. I think the part of the takeaways from this is going to be naming your outputs consistently and giving yourself kind of a nice working directory. It makes it cleaner to understand where your files are, what you named them, and avoiding poor situations in which you overwrite your file names with something else. And the only way to really know that is to understand whether the command like fsl mean ts has like an explicit option here or flag here to specify the output name, or if it's something like fsl maz where the output file name is just at the end of the, or it's the very last argument to the command here. So, and this will just be dependent on whatever command line utilities that you're using, whether or not they have a flag to like a flag like -o to specify whether or not it should be output using that file name, or if you just want to output it just with a like argument position, and that's usually at the end of all the other arguments. Yeah, I can also put this in a different directory if I wanted to, so just pre-pending the lab directory. Say if I wanted to put this in the 01 lab, I could put it in there, and it would output in that directory instead of right here. So, in fact, I'll just do that real quick just to show you the difference. So 01 lab OSF share. So if I run this again, it is now in 2 directories, and I'll demonstrate that in the terminal. So if I do Control-Shift-T, which puts me in a new tab, then if I cd 01 lab, cd OSF share, LSL, well, you can see the one, I guess the standard dev mask does exist in here. Yeah, which is fine, because that's where I saved it from the GUI. But now I just made the mask right here. Actually, how did that work? Actually, did it save in 2 places? Now that I'm looking at the standard dev mask, let me see in lab 02 if it's there too. Oh no, oh, that was the mess that I saved back. Okay. Alright, it all still makes sense with the world. Okay, I thought I was saving the mean mask. Back in the 01 lab, it was a standard deviation mask. Okay, things aren't going crazy. Alright, I think that is all I have to show you. If you have any questions, feel free to reach out to me on Slack if you're having trouble with this lab still. Again, once you name your files and making sure that you name them in the way that you want to, and that you specify the input values correctly. Again, tab autocomplete is going to be your friend here. Yeah, then you should be good. As we'll see later on, like we're already getting a little bit of bloat here with the file names that we have. Imagine if we did this for many different subjects, then we'd have lots of bloat here. So later on we'll be talking about organizational standards as a sneak peek. But without further dragging on this video, I'm just going to call it quits here and say great job, everyone. Hopefully you can make changes if you haven't been able to make changes to your lab yet. Use this video, make changes, make the commits, send it back to me, and hopefully we'll be well on our way to lab 03.